Hey, good morning, everyone. Can learning assistants confirm they can hear me, please?
Yeah, we can hear you.
Thanks.
We can hear you.
Okay, so welcome to Physics 214. This is the first day of class for this course. In Physics 214, we're going to cover the topics of optics, relativity, and quantum mechanics. And just to go in a little more detail on that, those of you who took Physics 213 just saw fluid statics and dynamics, thermodynamics and waves. In this class, what we're going to cover are some of the things listed below here. So just to give some sort of highlights, one of the things we'll talk about is how a device called an interferometer provided the most important negative result ever in physics. By negative result, I mean tried to find something and didn't. It was something that floated on a ton of mercury, but it was the inspiration for a device that allowed us very recently, in the last few years, to discover gravitational waves, which has opened a whole new realm in astronomy. We'll also talk about, for example, why spy satellites can't see everything. We'll show how you can make images that appear to float in the air. We'll talk about, when we discuss relativity, why one person can say two events happened at the same time and another person can say that they didn't. And both of those people can be 100% correct. It sounds like a logical contradiction, but it isn't. And then we'll talk about the scary possibility of how you could become older than your parents. When we talk about quantum mechanics, we'll describe when particles behave like waves. We'll talk about why the minimum energy that a system can have is not zero. We'll describe briefly an equation called the Schrödinger equation, the solution to which is the foundation of all of quantum mechanics, just like F equals ma is the foundation to all of Newtonian mechanics. And just like F equals ma, it basically came out of nowhere. The person who discovered it, Schrödinger and Newton, basically came up with it out of thin air. And we'll also talk about, for example, how particles like electrons can violate the hallowed law of energy conservation. So a little more specifically, the things we're going to cover for about 2.5 weeks will be optics, and this will be split up into two different pieces. The first piece will start today, called wave optics, and there we'll cover wave phenomena like interference and diffraction, and also interferometry, which is the technique that uses interference. We will also talk about ray optics for the next part of our discussion of optics, where ray optics is when we treat light as somewhere between being a particle and a wave, and talk about how light reflects off of surfaces, how it bends when it enters material like glass from a material like air. Then we'll spend a week on special relativity, which is algebraically quite easy, but conceptually can be pretty challenging. We'll then spend a couple of weeks on quantum mechanics, talking first about the photoelectric effect, which is the discovery that Einstein explained, and he explained it so well that he was given his Nobel Prize for that discovery, and not for the discovery of special relativity, which was arguably a much more important discovery. We'll talk about a basic model of the atom, focusing on hydrogen because it's so simple. We'll talk about wave functions, which are the solutions to the Schrödinger equation, and the concept of uncertainty as proposed by Heisenberg. And finally, as a model that proves to be very useful for understanding how the Schrödinger equation works and how quantum mechanics more generally works, we'll use something called particle in a box. And finally, at the very end, we will talk about atomic and probably also nuclear physics, choosing a few topics from those subjects that are pertinent to quantum mechanics. Okay, so I need to do a little bit of logistics now. So the course instructors are yours truly, and my focus is on the physics content. And Dr. Van Hook will cover all of the course administration. So if you have a question about how to do homework, or how to access an exam or whatever, Dr. Van Hook is the person to ask. You can send me an email to ask the question, but in 99% of those cases, I forward the email to Dr. Van Hook because he's the expert. Someone has just asked if these lecture notes are posted on Canvas. The answer is yes, and I'll tell you exactly how I'm going to do that in just a minute. That picture of me there is taken at the South Pole in Antarctica, where I work with a number of other physicists and astronomers on an experiment called IceCube. It was taken 8 years ago, and that sign I'm holding there is the day's temperature and weather. And you can see there's a smile on my face, and you can see from the temperature that day, which is -73 Fahrenheit with wind chill, that smile was basically frozen on my face for a while. There will be learning assistants in this class. There will be 4 learning assistants helping us in this section of Physics 214. They're listed here. The learning assistants are undergraduates who have volunteered to help with understanding the material, and in particular during class. So they may answer your questions in the chat, and they will also be in breakout rooms whenever we make those breakout rooms, and they'll be there to help answer questions as well. Okay, so I want to briefly spend a few slides talking about what I do when I'm not teaching Physics 214. As I already mentioned, I work with a large number of physicists and astrophysicists using high energy neutrinos to try to understand, first of all, the basic properties of those neutrinos, and also to use them as what are called astrophysical messengers. So the figure down at the lower left, which I'll blow up here, is an aerial view of the IceCube detector at the South Pole. There's not much going on there. It's basically an ice cap 3 kilometers thick, and there's just a lot of snow everywhere. We have buried roughly over here somewhere in the ice 5,000 photosensors spread out over a cubic kilometer of ice, and we're using that to detect neutrinos. I'll talk more about that in a minute. Here at Penn State is headquartered something called AMON, which stands for the Astrophysical Multi-Messenger Observatory Network. And what AMON does is it brings together signals in real time from a variety of particle astrophysics experiments, including IceCube at the South Pole, and tries to see if there are any coincidences in the signals that are arriving in the direction from which those signals came from and the time at which they arrived. And if there's a coincidence in direction and in time between, say, a neutrino detected by IceCube and, I don't know, a high energy photon detected by the Hawk experiment in Mexico, then we send out an alert to the broader astronomy community and suggest to them that they might want to look over in this position in the sky to see if something interesting is happening there or not. Okay, so neutrinos, one could spend an entire course talking about them, and I'll just spend one slide here giving you the basics. So they're fundamental particles in the sense that in the standard model of particle physics, a picture of which is shown on the right here, there are 12 known fundamental particles. Fundamental means they don't decay. They're, as far as we know, they're not divisible. They're not made up of constituent smaller particles. There are 6 so-called quarks, 2 of which, the up and down quark, make up most of nuclear matter, like neutrons and protons. And then 3 of which are called leptons, charged leptons. The one that's certainly familiar to you is the electron. It's basically responsible for most of chemistry. There's also a particle called a muon and a tau, which are also charged, and they're basically heavier cousins of the electron. Muons are fairly common. In fact, 1 muon from the atmosphere goes through your body every minute or so. And then associated with each of these charged leptons is a neutrino. So there's an electron, a muon, and a tau neutrino. And so neutrinos make up fully, if you look at this list here, 3 of the 12, or 1/4 of the fundamental particles that are known to make up all matter in the universe. Unlike their other quark and lepton cousins, the neutrinos are very, very light. So far, their masses have been too small to measure, although we know that they're non-zero by virtue of other measurements. They're also everywhere. So there are 300 neutrinos in every cubic centimeter of space. That's everywhere in the universe you go, you will find 300 neutrinos. The only exception to that is right near, for example, nuclear reactors or right near the fusion reactor in the core of the sun. There, the neutrino density is much higher. But on average, there are 300 neutrinos in every cubic centimeter of space. As far as we know, neutrinos don't decay. So they are indeed stable. And they're very, very penetrating particles, which is a good thing because with so many of them around, if they weren't penetrating, if they interacted much more than they did, we wouldn't be around to talk about it. There are 100 billion neutrinos going through your thumbnail every second. And most of those are neutrinos that are left over from the Big Bang. The neutrinos that go through my thumbnail going vertically downward right now, many of those will continue going through the Earth and come out the other side, moving at roughly the speed of light. So we're basically swimming in neutrinos, and so is the Earth, for that matter. Neutrinos at really high energies are pretty rare. They're also a bit easier to detect. And we found a source of one of these neutrinos with the ice cube experiment at the South Pole a few years ago. And what's conjectured to have produced this neutrino is a black hole, which is shown right here at the center of this figure, that was emitting a jet of particles, and that's shown here. And 4 billion years ago, it pointed this jet at where Earth was going to be 4 billion years later, just by chance, and sent out a really high energy neutrino. It probably sent out a whole bunch of stuff, but we detected the high energy neutrino and were able to point back to the location of this very energetic astrophysical object in the sky. So that was the first discovery of a source of high energy astrophysical neutrinos. I also use neutrinos to monitor reactors in order to enhance the process of nuclear non-proliferation. There are more details at that website there. This experiment is located very near Whitby in Yorkshire in UK. So there's a picture of Whitby. It's a very pretty little town. And unfortunately, where we're going to spend most of our time is in a laboratory called Bulby Lab, which is just outside of Whitby, but it's underground. So this is the kind of scene that we'll get to see most of the time while we're building this experiment. It's a kilometer underground, located approximately 25 kilometers away from a nuclear reactor site. And we're going to use the neutrinos from that nuclear reactor site to demonstrate that this type of technology can work to detect undeclared nuclear reactors from a significant standoff distance. So you could imagine monitoring reactors in countries that would otherwise not want you doing that, because you could do it from across the border in a friendly country. Okay, for the last 15 years or so, I've been the advisor for a group called PHYS, which is now called PHYS+. It stands for Physics and Astronomy for Women, and the plus sign means that they've become substantially more inclusive recently. Here are some of the things that that PHYS does, and up here are some URLs that you can use in order to learn more about this group, and I encourage you to reach out to the current members of PHYS if you're interested in joining. Okay, quick summary of some key course information. So the textbook is a picture of it shown here. I have a copy that I'm showing here in the video screen, so that's what it looks like. This is a custom edition for Penn State. So it just has the chapters that are relevant to Physics 214. It's from the 4th edition of the Knight book. And it's bundled with Mastering Physics, which is what we're going to be using for the homework. You may also have access to the complete 4th edition, which has, you know, all whatever 45 or whatever chapters. That's kind of a behemoth of a book. That's fine to use that as well. If you want to save some money and use the 3rd edition, excuse me, that's also fine with me, but just be aware that there have been some changes in the chapter numbering, and some of the sequencing moves around. Labs start next week. The exams will consist of 3 quizzes plus a final. The final will basically be 2 quizzes back to back. The quizzes will be spaced by roughly 2 weeks, covering the previous 2 weeks of material. And all the details for these quizzes and the final will be on Canvas. There is already posted an equation sheet, which you're welcome to use as you work through the homeworks, for example, and will be provided to you when you're taking the quizzes. So you don't need to memorize formulas. The homeworks, as I mentioned, will be administered via Mastering Physics. The grading scheme, which I won't go into detail here because it's a little bit complicated, but it's detailed on the syllabus, is put in place explicitly to encourage you to try every problem without worrying about losing points and worrying about not getting a perfect score on the homework. And I really, really strongly encourage you to try hard on these problems. You are welcome to work with other students if you like, but if you find yourself in a situation where the student or students you're working with are just giving you the answers to the questions, you may think that that allows you to understand the questions, but it doesn't. You really need to work through these yourself. So if you're in a group that's, and you find yourself being explained to much more than 50% of the time, I would switch groups and try to find another group or another person with whom you can work where your levels are more equal and you're able to communicate back and forth and help one another. You will learn a lot by teaching, and you'll learn better if the person who is helping you is not just giving you the answer. Okay. Generally, homeworks will be due Monday nights, just before midnight. No late homework, excuse me, is accepted. So please be very careful that you don't wait until the very last minute to submit the homework, because there are other schools up and down the East Coast and in the Eastern time zone that use the same day and time for the due date of their homework. I don't know how many. I didn't intentionally schedule it for that reason, but sometimes the website can get bogged down. So it's better to submit earlier than 11:59 p.m. if you can. There will be possible adaptive follow-up assignments given that are going to be due 48 hours after the main assignment. These are much, much shorter assignments, and they're focused on the elements of the main homework assignment that Mastering Physics has decided you need a little additional help with. Again, we can't accept any late adaptive follow-up. And please note that you need to attempt all the problems in the main assignment and reach 85% or higher as your total score in order to get exempted from the adaptive follow-up. So you get exempted and you get full credit, not just if you get 85%. So if you work through the questions and you've gotten 85% and you say, okay, I'm done, I'm gonna go off and do something else, and you just don't even look at the other 15%, Mastering Physics is going to say, this person has to do the adaptive follow-up because they didn't try all the problems. That's just the way Mastering Physics is set up. That's not the way I would have set it up if I had the choice, but that's the way they do it. So just be warned that you need to try all the problems if you want to get exempted from the adaptive follow-up after getting 85% or more. People occasionally have trouble with their browsers. Particular browsers don't work so well with Mastering Physics, but there's a link that's provided here that you can use if you're having some trouble. There are pre-lecture questions or PLQs that are administered via Canvas. These are going to be due Monday and Wednesday nights before class. They're based on the reading. You'll find that they're pretty simple. They're mainly to encourage you to read in advance before you actually come to class or to Zoom. I think that the PLQ that would normally have been due yesterday, since yesterday was, technically the course hadn't started yet, is due tonight. So please look at that. There will be Zoom polls during class, which are going to be graded for participation only, so don't worry if you get the wrong answer. But do note that unlike with the clickers, once you select an answer in a Zoom poll, you can't change it. So unfortunately, that makes it a little bit harder to change your mind. The slides, someone asked whether slides would be available. The answer is yes. So there's going to be a pre-lecture version that's posted before class, usually 24 hours, but always the night before. And then there'll be a full version posted after class is done. The preliminary version that's posted basically has all the questions that are posed during class without the answers. And then the full version has the answers included. And there also will be a link posted to the recording of each class. And I have to note that if there are any discrepancies between Canvas and these slides, Canvas wins. Okay, so I tried to make the two completely consistent, and I think I succeeded. But if there's any place where there's disagreement, then Canvas is the right place to is the source. So that's what's correct. Okay, you should come to your assigned lecture section. There's another lecture session at 8 a.m. That's how we're going to do the participation grade. You're encouraged to ask questions during these Zoom meetings via chat to the LAs or to me. The LAs are very good at answering questions quickly during the chat, so that can be a good way to clear up any small problems or issues that come up during class. I am also going to provide some incentive for asking questions in the form of extra credit. So if at least one good question is asked by a designated group of students, and that group will be different in each class meeting, I'm going to add 0.05% to everyone's final course grade, up to a maximum of 0.65% added to everyone's final course grade because there are 13 class meetings. 13 times 0.05 is 0.65. and that'll start next week. And the designated group of students is going to be done by the first 2 letters of your Penn State user ID. Choose something like 20 students at a time in each class. Okay, so just a word now about my teaching philosophy and the technique that I try to use. So everything that I've read about learning and cognition says that active learning is really important. It's a challenge to do active learning with Zoom. I'm going to try the best I can to do that. They also cite pretty strong evidence for seeing sort of new subject matter in lots of different ways, because that way you are able to make more connections to the material. This to me was a little counterintuitive, because if you see things lots of different ways, doesn't that get confusing? But the research shows that that's not the case. The more ways you see something, the better. It's very effective. And so there will be a lot of assignments basically in this class. So there are reading assignments. There will be these low stakes quizzes, the PLQs. There's these lecture presentations where we go through problems, in-class questions and discussions. There's the homework that you'll be asked to do. And I would, again, strongly encourage you to do the homework on your own first. And then if you have some friends you can work with them, provided that they're not just giving you the answer, and conversely, that you're not just giving them the answers, because you're not helping them by doing that either. And one of the curious things that I heard helps is explaining things out loud to yourself. So if you want to bother your parents or your kid brother or sister, here's a way to do it. Go around the house explaining things out loud in physics. And then there's labs that you'll be doing as well as the exams themselves. So the goal is not to overwhelm you, but to sort of nudge you in the right direction. But you are really strongly advised not to allow yourself to fall behind in this class. You should really put in regular effort. It will be pretty difficult to catch up because it's just a half semester class. So if you miss the first 3 weeks, that's half of the class. Okay, I am now going to jump over lots of slides and go directly to a review of wave interference. Those of you who took Physics 213 either just this past 7 weeks or in an earlier semester will be familiar with this. And those of you who even haven't may have seen this also in other physics classes or engineering classes. So the setup for interference in one dimension is to have 2 waves going in the same direction. So the 2 waves could be doing this, moving in the same direction. So that my hands are one behind the other here, and there are 2 waves going in the same direction, say the x direction. The waves, for simplicity, are identical in the sense that they have the same wavelength and the same amplitude. The sources could be physically separated by some distance, or they could be in phase with one another or not. So what that means is, so if I have the 2 sources, here's one source here producing a wave, here's the other one here, they could be separated by some distance like this and producing waves. So they're separated along the x-axis. I hope people can see the video here because I have my hands up in the air trying to demonstrate this. And they could be in phase or out of phase. And what that means is if we have these 2 sources here producing waves, if they're in phase, then that means they're both going up and down at the same time. So they're both producing, say, sound waves that come out in phase with one another so that the peaks line up with the peaks and the troughs with the troughs. Conversely, you can also have waves that are completely out of phase, in which case, when one goes up, the other goes down. So it's going to look something like this. Or we could make it look like this. One goes up, one goes down, and up and down like that. Okay, so what happens when these 2 waves that are traveling in the same direction overlap with one another? So in order to figure this out quantitatively, we add the expressions for each traveling wave to one another. And in general, the expression for a traveling wave, which depends on position and time, is equal to the amplitude of that wave times the sine function with the argument kx minus omega t plus some phase. And so this expression here tells you the amplitude of this traveling wave. K tells you the wavelength, because it's equal to 2 pi over lambda. Lambda is the wavelength. And omega is 2 pi times the frequency. It's just the angular frequency in radians per second. And the velocity at which this wave moves through space is given by omega divided by k. Okay, so if we take two waves, two traveling waves, and they're labeled here D1 and D2, and we add them together, then we're basically adding together two sine functions. And there's a way to do that using this trigonometric relation written down here. If you do that for these two traveling waves, then what we get is this expression down at the bottom. So let's explore the details of that expression. The first term in brackets here does not depend on time, and it gives you the total amplitude of the wave everywhere. And the second term has a sine function with this telltale kx minus omega t term, which tells you that this is a traveling wave. And furthermore, it's a traveling wave that has the same wavelength and the same, well, actually wave number is what k is. So it has the same wavelength and the same frequency as the original two traveling waves had. So we have the sum of these two waves, D1 plus D2, gives you a traveling wave. It has the same wavelength and frequency as the two contributing waves, but it has a different amplitude. The amplitude can vary here between 0 and 2a, as shown, because this cosine term, let me clean things up a little bit here, it's getting a little messy. This cosine term here can vary between plus and minus 1. So the amplitude can vary between 0 and 2a because of that. Well, technically minus 2a and plus 2a, but the amplitude for these waves is the distance that is defined as the distance from 0 to the largest magnitude value, which is 2a. All right, so let's focus on this delta phi term inside of the cosine. So in particular, we're looking at this piece inside here. So that's written out down here. It's the difference between those two arguments. And you can see right away that these terms that depend on time cancel one another. We have a minus omega t from the phi 2 term and a minus omega t from the phi 1 term. So we have minus omega t plus omega t, and those just cancel each other out. So there's no time dependence. That leaves terms that depend on position x and this phase constant. So in order for delta phi to attain special values, so remember we're looking at a cosine of delta phi over 2. So what are the special values that you think might be of interest here for cosine of some argument? So what are the special values of cosine? Special is a subjective term, of course. So one special value is 0. If you have delta phi set to the right value, you get the cosine of delta phi over 2 to be 0. Another special value is plus or minus 1. And these are special because the 0 is minimal, and the plus minus 1 gives you, the maximum, in this case, maximum amplitude. And in fact, what we'll see is that when this is 0, when cosine of delta phi over 2 is 0, then we will get what's called destructive interference. When it's plus minus 1, we'll get constructive interference, where in the first case, the two waves basically look like this, and the second wave might look like the following, like that, and they essentially cancel each other out. The same amplitude, same frequency, so the peaks line up with the troughs and the troughs with the peaks, and you end up with basically the following, flat line, nothing. Whereas with constructive interference, what you would get is one wave like this, a second wave that is right on top of that wave. I'll just try to draw it without obscuring the previous one. And so the sum will look like something with twice the amplitude. Okay, so the way we can get cosine delta phi over 2 to be one of these special values is, more generally speaking, how do we change the relative phase of these two waves, these two traveling waves that we're adding together. We can either do that by having their sources emit the waves out of phase. That gives you destructive interference. Or in phase to get constructive interference from the same position. So let's just focus on destructive interference first. So in order to get destructive interference, this term delta phi over 2 needs to satisfy this expression here. So what this expression tells you is that delta phi, let's say m equals 0, delta phi will be equal to pi. If I put in m equals 1, what do I get? M equals 1 means 2 times 1 plus 1/2, 2 times 3/2 is 3, so that's 3 pi, and so on. And if I take pi, 3 pi, all these values, and put them in to the cosine delta phi over 2 term, then I get cosine of pi over 2. I get cosine of 3 pi over 2. And these are all equal to 0. So in other words, whenever delta phi is equal to 2 times m plus 1/2 pi, where m is equal to 0, 1, 2, etc., then cosine delta phi over 2 is equal to 0. And then the amplitude of this wave function that we wrote down here, cosine of delta phi over 2 is equal to 0. Then that means that the resultant wave, we're summing these two traveling waves together, D1 and D2, is equal to 0 everywhere. That's fully destructive interference. So you can get this in two main possible ways. The first way, which is shown here, I'll just blow it up so we can see it a little more easily, is if the two sources, 1 and 2, emit the waves 180 degrees out of phase with one another, or synonymously pi radians out of phase with one another, but from the same position. So these are both at delta x equals 0, or I should say these are both at x equals the same value, so delta x equals 0. If I drew, I don't know, an axis here, here's the x-axis, and here's x equals 0. So they're both at x equals 0. Okay. If one speaker emits the wave I don't know if you know how loudspeakers work, but they're basically a cone that moves in and out like this, okay? And it produces sound waves. If you have two speakers side by side and they're in phase, then they're both moving in and out like this at the same time. If they're 180 degrees out of phase, then they're doing this. So if they're 180 degrees out of phase, which is drawn in this figure A here, then the troughs of one sound wave produced by speaker 2 line up with the peaks of the sound output by speaker 1. And consequently, what you'll get is fully destructive interference. If you just had speaker 1 on, you would hear a tone. If you just had speaker 2 on, you would also hear a tone. If you put the two speakers on simultaneously and their phase difference is pi, they're 180 degrees out of phase as drawn here, then you will hear nothing. So the two waves will destructively interfere and there will be zero. And someone mentioned, is this how noise canceling headphones work? And basically the answer is yes. There's a little sensor in the noise canceling headphones, and it hears the outside noise, it inverts the outside noise and adds it to what you're hearing through, whatever you're playing. And then the sum of those two things, the outside noise that gets in plus the inverted sound that the circuitry in the noise canceling headphones makes, cancel one another. And so you end up with just the music. Okay, another way to get destructive interference is to move one of the sources relative to the other. So here the two sources are separated by a distance that's equal to 1/2 of a wavelength. And in that case, again, the troughs of one waveform line up with the peaks of the other, and the peaks of one line up with the troughs of the other, and you end up with cancellation. And of course, you can take some combination of these two effects, or these two ways of changing the phase. You can have a phase difference of pi/2 at the generation and a separation distance that's, say, 1/4 of a lambda, and then you will end up also with fully destructive interference. Okay, I didn't show it here, but you can also draw similar pictures for how you can get fully constructive interference. So I just focused on destructive interference here. If you want constructive interference, then you want this cosine delta phi/2 to be equal to ±1. And so in order to get that to be the case, we want the delta phi/2 to be an integer multiple of pi. Okay, so you want the argument here, you want to get cosine of pi or cosine of 2 pi. I guess I should add cosine of 0 as well, etc. Those are all equal to 1. So if we get delta phi/2 to be equal to 0 or pi or 2 pi, then we will get fully constructive interference. So that condition will look different from this condition here, and you can write that down on your own. Okay, so that's the end of the review. What I'd like to now get into is wave optics. So what we're going to talk about now is how light behaves like a wave, because it can behave like either a wave or a particle. And what I have shown here are two different cases. One where traveling waves behave like waves, and where traveling waves behave like particles. Or maybe a better way to put that is on the left-hand side, this figure here, I'm showing some clear wave behavior. And That's shown by these water waves in this case. The peaks are separated by this distance, and they go through an opening which is comparable in size. So this opening from here to here is comparable in size to the wavelength. And when that happens, the waves that come out the other side get kind of bent around or circularized. So even though the wave was traveling purely in this direction, we now have waves that are traveling at a different direction. So the disturbance somehow manages to go around the corner here. By contrast, this figure over here shows light behaving like a particle. So the previous picture was water behaving like a wave, not surprising. And here, this is also not surprising that light behaves like a particle. And the main reason for that is because the wavelength of light is like a nanometer, or sort of on that order, 100 nanometers or something. And this opening here is obviously about 1 meter. So the opening is much, much larger than the wavelength of the light. And so what you get is basically this sharp outline, and you don't see any light, over here or over here. So the light doesn't spread around the opening like these water waves spread around the opening as shown here. Okay. So one of the main ways that we can get light to exhibit wave behavior is by passing it through an opening that's comparable to its wavelength. And so I'd like to show you an example of this using the following demonstration. So first, what I want to do is show you, whoops, clear this. So these are two wave sources, and I want to show you first interference. So these are two sources of waves, basically, a green light that is emitting light continuously. And what we're showing here are the peaks of that light as it's emitted. And so this is a single source. Now, if I put another source on at the same time, and it's perfectly in phase with that source, then you end up getting this pattern that you see here, an interference pattern. These waves are now interfering with one another. We can produce the same effect as what we've shown here, where we have two identical sources emitting in phase from the same position along the x-axis, and we get interference. We can get a similar effect if we send plane waves through a barrier. So first, here we have plane waves, and they hit the screen at the far end, and that screen you can see is uniformly illuminated. And by the way you make plane waves is if you get far enough away from a source that's emitting spherical waves. If you're far enough away from it, then the little part of the sphere that you see is basically planar. So we're just very far away from a spherically symmetric source. It's emitting spherical waves. If we're really far away from it, then we're going to see these plane waves. Okay, so now what I want to do is send these plane waves through two slits. And if I do that, the two waves, or the two waves that emerge, are in phase with one another because the incoming single wave that's making it is in phase with itself by definition. So they hit this barrier with the two openings at the same time, and they produce an interference pattern just like the two independent sources that I showed you previously. The two independent sources were in phase by design. It's kind of tricky to get that to make two sources like that. It's much easier to do it this way, where you have a single source and you send them through two slits. Then you get them to be in phase when they arrive. And then the interference pattern is due to the different distances that the waves travel as they get to the screen. And you can see that the screen now doesn't have a uniform illumination, but instead it has some bright fringes and dark fringes. So I encourage you to play around with that if you get the chance. So let me go through the details of how this works out. Basically, the idea is that you have these, and I'll finish up in just a second. You have these waves coming in as plane waves from the left. And then when they come through, they basically get bent or circularized, if you will, because they're passing through openings that are comparable to the wavelength of the light in this case. And then as they travel, they overlap with one another, and along this line here and along this line here, and all these lines, they interfere constructively, these two sets of waves coming out of here. And so you end up with a bright fringe wherever that constructive interference has occurred. So I've circled a few of those cases here. This is due to the following geometric effect, namely that light from one slit is traveling a distance r1 in order to get to the screen that's far away. Light from the other slit is traveling a distance r2. And those two distances, r1 and r2, are not exactly the same. In fact, they differ by this little distance here. Okay, that distance is equal to d sine theta. We'll talk more about this next time. If you have any questions about the course, you're welcome to stick around afterwards, and I can try to answer those questions then. See you next time.
Excuse me, I got a question.
Yeah.
Can you tell me when is the grade of Physics 213 released? I mean the final one. The final grade.
The final grade for Physics 213, is that what you asked?
Yes.
I'm not entirely sure. It should be pretty soon. There are still some people who haven't taken the Physics 213 final, so we certainly need to wait for them. Shortly after the grades on the final are released, we will be submitting the final grades. So I would guess, in about a week.
Okay, got you. Thanks.
But I don't know how long it then takes for the registrar to release them,
I know.
to you. But I think the unofficial grade, we'll be able to post that to the Canvas website or wherever the grades get posted in about a week.
Okay, thanks. Have
You're
a good
welcome.
day.
Sir, this week homeworks are due on mastering physics.
Please have a look at the website. I think that there's this practice of mastering physics, how to use mastering physics, that is optional. And I know you just took Physics 213, so you don't need to bother with that. I can't remember if there's an assignment due on Monday, but you should really look on the website.
Okay, thank you, sir.
You're welcome.
In regards to the Mastering Physics, is there like a bundle where the textbook comes with Mastering Physics, or is like through the website, the e-text, or do we have to go to the bookstore to get that?
I'm pretty sure you can get the electronic version bundled with Mastering Physics.
Perfect, just like 213.
Pardon me?
It was just like 213, right? Just a
Yes, it
bundle
should be
together.
just like 213, yes. Mm-hmm.
Perfect, thank you so much.
You're welcome.
Will the Zoom links for the labs be posted before lab next week?
Yes. I'm not sure how soon before the lab, but they'll definitely be listed before the lab.
Where should we expect to find that then?
If you go to the Canvas site, there's a link for labs, and it should be there.
Okay, sounds good. Thank you.
You're welcome.
What time will be lab?
Can you repeat that, please?
What time and what day would the lab be on? I didn't see it posted on LinePath for some reason.
Yeah, you should know what section you're in, and that'll tell you what time you're to meet.
Okay, it should come up on the LinePath schedule then?
I believe so, yeah. If it doesn't, then you should ask Dr. Van Hook, because I'm
Okay.
not entirely sure
All
how
right,
that's
thank you.
managed.
Professor, where can I find the attendance poll?
So there is no attendance poll per se. I do polls usually, but not always during class. And,
Okay.
and then it's just participation that people get graded on.
So it depends on the class, right? Not every class will have like a
Yeah, I mean, today was unusual because I covered a lot of, logistical material. In pretty much every class, there will be a poll or one or more polls that's done.
just like clicker questions in class, right?
Exactly.
Oh, okay. All right, makes sense. Thank you, Professor.
Yep, you're welcome.
So does that mean we could join any section?
I'm sorry, can you repeat that? I didn't hear the beginning.
Can we join like any of the sections at a different day, like 8 or 9, depends on like which time is best, or do we have to just like attend one of them?
I'm not 100% sure about the participation grade. I think it'll probably be okay if you attend either section. I think also that it's probably pretty trivial to change the section if you want to.
Because I could do 8 on Tuesdays. I would rather do 9 on Thursdays.
Oh, so you want to do a different time on Tuesday and Thursday?
Yeah.
I mean, I think that should be okay, but let me, can you send me an email about this and then I will ask.
Yeah, because I got work on Tuesdays, so I got to do it early, but then Thursday I work late Wednesday, so I want to do the later session. I'll send you an email. Thank you.
Yeah, okay, yep.
Dr. Cohen?
Yes.
I have 2 questions. So today I am scheduled for a lab. Do we have lab today, being that today is the first day of class?
No, lab starts next week.
Okay. And then I have a question with regards to diffraction grading, because when I was taking the PLQ, I got stuck on 2 questions. And I wanted to ask you, because when it comes to diffraction grading, I thought of it as like how like the way chemists do it when determining elements within a gas, like how they look at like those papers. But I wasn't necessarily, I don't remember if it was called that or not because I haven't taken chemistry in so long. And then when you were saying it just now, when it comes to the diffraction, when you're having a beam go through the slit, it's that distance of that sine theta, that r sine theta, like that difference in distance. Does that cause that diffraction for like illuminating the light on the screen?
Yes. So a diffraction grating is kind of a misnomer. It really should be called an interference grating. And it's basically, I don't know if you can see the screen here.
Yeah.
It's essentially what you see here, except instead of just having 2 slits, you have a very, very large number of slits, or a very, very large number of sort of scratches, that are nice, that are, maybe scratches is not the right word, grooves that are dug into some material, very closely spaced together. And then when you bounce light off of it at a particular wavelength, you will get constructive interference on a screen far away at a particular place. And so that allows you to separate out the light that is emitted by a chemical substance, for example, when it's heated. So when you heat up a substance, you excite the electrons chemically, and then when they de-excite, they emit light at a particular wavelength. And depending on the material, the wavelength that's emitted will be different. So if you send that light that's created through a diffraction grating and then look at the wavelengths that you see on the screen, you can use that to chemically identify what materials produce the light.
Wow. Okay. All right. Thank you very much.
Sure. And we're going to cover diffraction gratings in a bit more detail in the next few classes or so.
All right. Thank you very much. Have a great day.
You too. Any other questions?
I have a question.
Yeah.
Oh, sorry. Give me a second. Okay, so is Physics 213 a prerequisite for this class? I came
No.
from 212.
No, Physics 213 is not a prerequisite. That's why I went through that review just initially, because that was something that we just covered in Physics 213, but I'm not assuming that everybody was in 213, so I'm covering it again here today.
Okay, thank you.
Yep, you're welcome. Any other questions? Okay, I'll see everybody next week. Bye-bye.